the force per unit length between current carrying conductors. Okay, so that's the formal definition of current. Now that's current. The next portion is resistance. Resistance. How is resistance defined? Again, resistance can be defined as how easy it is for charges to travel across a device in a circuit. So let's see how, if you turn to page 5. So electrical resistance is a measure of how easily a charge flows in a material or any kind of a resistive device in a circuit. And the formal definition, or this here, should also be sufficient for the students. If the students were to define it like this in the exam, it should be sufficient given that they have explained what each of these terms mean. So resistance can be defined as the ratio of the potential difference across a material in a circuit divided by to the current flowing across it. So this can also be another definition of resistance. Okay, and resistance here is measured in ohms. Okay, the potential difference is of course measured in volts. Current is measured in amperes, and resistance will be measured in ohms. Alright. The next portion is about resistance in terms of the resistivity of a material. For example, this is pretty familiar for the students. The students should be familiar with this from IGCSE. Resistance is directly proportional to the property of a material called resistivity, which depends on the kind of material it is, for example copper, steel, etc. And then it's directly proportional to the length of the resistor, and it's inversely proportional to the cross-sectional area. Okay, so the students should be familiar with this. If they're not, you can go into the details of explaining how and why this happens. State Ohm's law, 5.1.8. So Ohm's law, you should know that Ohm's law states that for fixed physical conditions like temperature, etc., temperature, light, etc., you should have that the voltage, the potential difference across a resistor is directly proportional to the current flowing across it. Now, not all resistors will follow this, okay? But the resistors or the devices that do follow this are called ohmic devices. Okay? You should know that in real life, there are not a lot of ohmic devices because most of them have varying voltage versus current characteristics, especially as the temperature and the other physical conditions change. But almost all resistors do behave like ohmic resistors within a certain range of temperature and within a certain range of voltage and current. Okay? So that's Ohm's law. Compare ohmic and non-ohmic behavior, 5.1.9. So 5.1.9, you should make the student familiar with a few graphs on page 7. There are a few different characteristics of a filament lamp, thermistor in part D, and a junction diode. I think they should definitely know how and why a filament lamp behaves like this. Again, usually the graph that is given is an IV graph, not a VI graph. Okay, so a filament lamp will have characteristic like this. Why? Because as my potential difference increases, my resistance should increase. Why? Because when the potential difference across a filament lamp, which is just a bulb, it increases, the temperature will increase, and therefore high temperature always means higher resistance. So, well, not always, but in this case, most conductors like this would have a higher resistance with high temperature. So, at a higher temperature, you should have a higher amount of resistance. you can see that the voltage goes on increasing at a higher rate than the current. So therefore the V over I value will go on increasing. Okay? So that's why a filament lamp IV characteristic looks like that. What else in this part? You should have compare ohmic and non-ohmic, derive and apply expressions for electrical power dissipation in resistors. Okay. So power dissipation. So obviously when charges dissipate energy in resistors in a circuit, they are obviously dissipating power as well. Power would simply be the rate at which this energy is dissipated. So power is defined as work done over time. Work done, in this case, work done by the charges. Okay? And the work done by the charges in going through a resistor will be defined as the amount of charge multiplied with the potential difference across the resistor. Okay, so Q over T here is going to be the current. Okay, so this would be the definition of power dissipated in a resistor. When there is a current of I flowing through it and there is a potential difference of V through it. Now, I can also be written as V over R, right? So therefore we have the power given by V squared over R. This is handy when you don't have current information. Okay? And again, V can be written as IR. So power can be written as I square R. Now this form of power is useful when you don't know the potential difference but you have the resistance and the current information. Okay, so that sums up 5.1, and a part of 5.2 we will now go on to 5.2. Okay, 5.2 electric circuits. So 5.2.1 is defining the electromotive force, which we've already done in the first part. The rest of this is simply about electric circuits and resolving circuits and their different circuit components. So again, this should be a familiar topic for everyone who has gone through IGCSE or their secondary level. Let's see. Okay, electric circuits. So we've already defined EMF. Now, the first thing that you want to talk about is batteries. So commercially available batteries or cells, they actually, those are the components that provide EMF in a circuit to provide energy to the charges, right? So they convert the chemical energy within the batteries and they provide energy, electrical energy to the charges. And that's how the charges flow and drive all the circuit components. Now, basically that's the source of energy in an electric circuit. But now, let's say this here is a commercially available cell or battery. Okay? This here is the positive terminal, this is the negative terminal. So this battery is providing EMF to a circuit. Okay? Let's say there's a resistance R over here. Okay? Now, in a practical case, there is always a little bit of internal resistance within the cell itself. Okay? Let's call that small r. So a little bit of internal resistance. Okay? So let's say that the EMF provided by the battery over here, okay, is the EMF supply. Okay? Now the voltage across the terminals of the battery is actually going to be slightly lesser than the EMF because of the internal resistance. Let's show that. Let's say the current flowing in the circuit is I and the EMF provided is, let me just write it as EMF itself. If you turn to page 10 over here, these are the notations that I used. Let's say the potential drop across this resistor is V1 and the potential drop across the internal resistance is V2. Okay, so we know that the EMF provided or the energy supplied per unit charge, okay, is going to be equal to the potential drop here and the potential drop here, or the energy dissipated per unit charge here and the energy dissipated per unit charge here. Simple law of conservation of energy. So we have EMF equals V1 plus V2, right? And we also know that V1 would be given by I multiplied with R, and V2 would be I multiplied with small r. Okay? Now, the potential difference across ends of this resistor must be the potential difference across the ends of the terminal of the battery, right? Why? Because there is no other resistance or circuit component between these points. So, the potential difference between these 2 points is the same as the potential difference between these 2 points, right? So, this then can be called the terminal resistance of the battery. The terminal potential difference or the terminal voltage. Okay, so IR will be equal to the EMF minus I small r. Right. This here is the terminal voltage. Okay. So the EMF supplied minus the current multiplied by the internal resistance. Okay. So if you actually see the terminal voltage, that's how useful this battery actually is to the external circuit, because the internal resistance is simply it's a hindrance to actually providing energy. So the lesser the internal resistance, obviously the better for providing energy to the circuit. So this here, terminal voltage, is actually showing you the usefulness of a source of power. Now after this, there are just a few examples of using this equation. Next is a topic which should be very familiar with most students. It's how to find the effective resistance of resistors in a series circuit and a parallel circuit. So if you have resistances in series, okay, let's say there are resistances in series and they are all connected to a particular battery source here, right? And the current is I. You should know that the effective resistance here, if this were to be replaced instead with one resistance called R effective, okay, right? So V would be equal to I R effective, right? And V would also be equal to IR1 plus IR2 plus IR3, right? So therefore, from these two we have IR effective equals IR1 plus R2 plus R3, right? And hence we have the R effective equals R1 plus R2 plus R3, okay? This formula holds no matter how many resistances we have in a series, okay? So this is for series circuits. If we have a parallel circuit,